we have, we've got, so the main ones are the odometry, which is where we've either measured or guessed that the robot's moved, and also the observations, which are the objects we've seen. And so with the observations, you can have any number of them in any frame. And so with the odometry, we've got a forward amount of movement, a sideward amount of movement, and a turn amount of turn. So you can see the coordinate system that's used up here. And for the object observations, we've got the distance, which is how far away the object is, the bearing, which is the direction from the robot, and then the position that that object is on the field, so the XY position on the field. And so all of these inputs have noise, and so basically the job of the common field is to try to figure out the best estimate based on knowing that. And so some of the additional inputs that the localization system uses, it uses the team information and the game information, at least in the previous version of the code. And so it uses these. So for example, the team information is used to tell whether you're like on which side of the field you're on. So before it used to be yellow goal and a blue goal, and so it used to read that to know what side of the field it put its models on when it started, because it tries to put them in a rough guess of where they are. So the other thing is the game information, and it uses things such as the signal when the ball goes out, when a robot gets penalised, so it uses them to, for example, when the ball goes out, you sort of know that it's going to be put back in a certain spot according to the rules, so it tries to move the ball model to that spot. When a robot falls over, it knows that it might not know which way it is, so it increases the uncertainty and that sort of thing. So just got a lot of little adjustments that you can make based on what you know about the game. And so at the moment, this is both of them. So I'm not sure if the team information will be as important now since the field's symmetrical, as long as they all think they're on the same side, I guess. And so basically the outputs of the system is we want to know the robot position, the ball velocity. And so by deduction, we can work out where the relative objects are based on from the robot. So the robot state is an X, a Y, and a theta. So the X and Y gives the 2D position on the field, and the theta gives the orientation of the robot. The ball has an XY position and an XY velocity. And so, so basically, a general overview of the Kalman filter, the way we use it is a state estimator. And so the way that works is we've basically got a box here, like a black box type thing, where we've got the state, the X, the Y, the theta. But we can't actually look at those directly. So we don't know what the X is, what the Y is, what the theta is. What we can look at is the observations that we can get. So we can get the observations are coming out, but because we know basically that the observations come from this state, so it's a function of the X, Y, theta position where a certain object is here. We can use these observations to try to guess what this state is inside the box. Sort of. And so the other thing you have is basically the inputs to the system, and this is kind of in the localization. This is sort of the odometry. So you can sort of assume that if the robot was in a certain position and we moved it by a certain amount, then the state should have moved by that amount as well. And so the idea of the Kalman filter is from this value and this value, we try to work out what that value is. And so let's just describe here the outputs and the inputs.
That's awesome. It was.
So there's basically two steps to the Karma filter. There's the time update or prediction step. In this step, what it does is it determines a new prediction of the state based on the previous state, as well as the measurements, in this case the odometry, and the process equation, which is basically how we know the system acts. So our equation that determines how the process changes over time. And then the measurement update happens after that, and that basically is a correction step, and that uses the observations, or the measurements we've obtained, which are these the observations of the objects, and we use this to try to correct that estimate. And so in the Karma filter, the estimate is given by a normal Gaussian distribution. So you can see that here, and that just gives basically a probability graph of where the likely conditions of the robot is. So of course in observation it's a multi-dimensional one. This is just a one-dimensional one, but it's represented using the mean, which is the most probable position, and then a covariance which describes the shape of this curve, how spread out it is. And so in the localization, it's a multi-dimensional one. So so here we've got like this is the mean would be an x, y, theta, and the covariance is a matrix that's got like x, x. So it's got it's like 3 by 3. So it's got a term for each of the it's got the three-dimensional distribution information. Basically, I'm just quickly, I'm not sure how many people are familiar with this stuff, so I'm just trying to cover it all of it. So basically, the system we're looking at is usually presented using space notation. And so how this works is you have an equation to give the next state from the previous state and the input, and then the output is defined by the new estimated state and the input. And so basically you have these 4 matrices. The A matrix is used to determine the component of the previous state that's used to calculate the new state. The B matrix is the component that the input that's used to calculate the new state. The C matrix is the component of the new state that is a part of the output, and the the D matrix is the amount of the input that is seen in the output. And so basically, like a really simple one would be if you've got say 2 states here, you might have an A matrix like that. So it'd be A. And then you've got, say, 1 input. Say best to both of them. So basically all this is 2 sets of equations to find the new x and the new y. And so the new x would be x equals xk is xk minus 1 plus 0.5 z, just by multiplying the matrix through, and then y is y half minus 1 plus 0.5 z. That's basically how those equations work, and a similar thing with the y.
Sorry if you've already mentioned this, but is this all in the discrete?
Yeah, yep. So that's in the discrete case.
Yeah.
Because of the case. It's a similar thing for the time, but don't need to go into that. Because we don't need to use those things.
Sorry, do those matrices need, are they tunable by us? Like,
Just wait till I get to the next bit. So we don't actually use those because they're not linear, that's the linear case.
Right.
So basically the time update is a future one, and so it uses this first one, which creates an estimated new state using the previous state and the input, and the measurement update adjusts the predicted state based on the object observations using the observation model, which basically none of our observations use the input, the odometry, to determine the object transfer. It's all based on the position. And so this is basically that matrix. And so basically for localizations, this is a linear version. For localization, it's not linear because of the orientation. So the orientation marks all this up, basically. So we have nonlinear functions here. So there's so the regular Kalman filter is a linear system. For linear systems, we need to use nonlinear Kalman filters for the localization, which include the extended Kalman filter or the uncentered Kalman filter. The uncentered one's the one we use at the moment. And so this has these. So instead of the linear functions, we've got these nonlinear functions. They notice they use the same things: the previous state and the input, and the predicted state. So these two are just the noise values, because basically every bit of information we get, we need to assume noise. And so these are the two equations that we have to make ourselves, basically, for any system that we want to use a Kalman filter for. And so the estimate is generated using the previous estimated state, measurements of any changes, and knowledge about the system in the form of the system model, which is A and B metrics in the previous ones, or this nonlinear equation. And the observations used to correct this estimate by comparing the expected observation based on the estimate to the observations you receive. So the way noise comes into it, so noise is associated with all the measurements you receive and also the process equations, because there's not many systems that we have a perfect system equation for that will always be, that you can track precisely over all the time. And so it's basically one of the most important tuning factors you need to get right to get the localization system running properly. And so basically the time update increases the variance in the system, and the measurement updates decrease the variance. So basically, whenever you do a new estimate, you're assuming that that estimate has actually made it a bit less certain where you are, because you're not quite sure that your odometry is correct, and over time things can change as well. And so, but when you do the corrections, that actually sort of helps make you more sure of where you are by giving you some feedback. And if it matches well, then you know that your estimate's likely correct. And so, for some of this is coming to sort of the more complex part. So for some of the observations, we have the distance and bearing information, but we don't actually know what the location of that object is. So for example, if I go back to the field, if you see a goalpost, you know your distance and your bearing to it. But if it's possible that it could be this one or this one, then you've got these two possible field locations that that object would be in. And so that gives you two different versions of the update, basically. So this is where the ambiguous problem comes in. And so in this case, we can end up with a list of possible locations for the object. And so the Kalman filter can only represent one Gaussian probability, but when you have two of these updates, you end up with a multimodal Gaussian distribution, which is you basically get two Gaussian curves because there's two likely positions based on each version of the measurement, for example, if it's an A or B type decision. And so the way we approach this is we use a separate Kalman filter for each of these Gaussian distributions. And so using multiple filterable color filters, we do the estimate. We base the color filter off the previous estimate, basically, and then do a different measurement update for each filter. And then we evaluate how close that update was to the estimated update, and use that to weight the system, weight that that version of the update. So you basically end up with a decision tree type thing like this. So this is just showing a binary decision, two separate decisions, and so you can see you start off with one estimate. You try two different updates. This gives you two new models. You then have another decision, you do another two updates, and so then you end up with four models. And so, so basically just by doing this, you can evaluate all the possibilities, and then later decide which one was the most correct. And so the problem with this is that the tree grows exponentially. And so we need to get rid of some of them, or else we'll just kill the robot basically.
Do we have access to like all the models that exist as well as their distributions?
Yeah, all the ones that
I'm just thinking from Brendan's point of view, it could be interesting to generate a heat map of probability where the robot is rather than those circles. Generate a full heat map.
New people already used to do that.
You do a heat map.
just shows them all separately.
But you can't heat map the same information.
Yeah, doesn't you just end up with a multi-modal? You can have a heat map where I think I am, which would be have a lot of information. That would be cool.
So basically, in order to limit the growth, we need to figure out some way to get rid of ones that are useless, basically, because you end up with lots of ones that are really, really low probability.
How many do we normally have?
About 8 of them, it keeps between frames. And
So
so,
we've done before actually for the competition.
and so there's two main methods. One is to merge them together, and one is to remove them. So merging is the idea that we have two distributions, but we want to try to represent it by one, because we want to reduce the number of Gaussians we're using to represent distribution. And so the merging is trying to preserve information rather than discard it. And so here's an example where this blue dash one and blue red one have been merged to create this purple one. And so it's, it joins two models together that are okay, it basically uses a metric to determine how similar the models are, and measures the similar ones to try to best encompass the entire data set. The other one is to just chuck them out. So one of the methods is to just keep however many of the best models. So here we've got 5 models with different weightings, and so we just pick the ones with the highest weightings and discard the other 2. So for example, this is to say keep 3 of the best ones.
So what does that weight represent?
The probability of that model being correct,
Given all of the observations.
so all of the alpha values should sum to 1. And so, okay, that's all of the basically the overview of how it works. So this is some of the more specific implementation stuff. So basically, with the localization system, we have a separate filter for the robot position and for the ball position. The robot position is in absolute field coordinates. The ball position is relative to the robot, using the robot's coordinate system. And so the absolute position of the ball is calculated from the robot model and the ball model. So if the robot thinks it's in front of it, then whichever way it's facing, the ball will be that far in front of it in that direction. And so that kind of works a bit better, because when the robot changes its estimated position, it moves the ball with it. And so generally, whenever you're seeing the ball, it's relative to the robot anyway, and so that's how it makes it, I guess. So this is the main steps of the localization system. The first one is it checks the game state. So this looks for those triggers I was talking about, like if the robot's fallen over, if it needs to, if it's the start of the game and it needs to reset the system, those sort of things, if the ball's gone out. The next one, it does the time update. So this uses the odometry and the previous state. Next one is to process the objects. So it performs the observation updates using all the visible objects. So basically it's better to do the known objects first and then the ambiguous ones to prevent producing more models. Because basically if you've got two models to start with, then you need to do, because the known objects get updated on every model the same. So if you have two, and then it's later split up into four, if you do the known objects first, you do 2 updates. If you do it later, you do 4 updates.
As a clarification, I'm not sure how many of you guys know, but
I don't know if you
when we can't see both goalposts, we say, well, I'm not sure which goalpost this is. This is an ambiguous goalpost. So then we have to check whether it's right or wrong for both goalposts in our model.
So then the next one is to do the shared ball update. This is the information the robots send between each other about the ball position. And then finally it writes all the information about the estimate back to the field objects part. And that's how the rest of the system accesses the localization information. That's like one pretty much. So there's a fair bit of redundant code that you could probably get rid of that I used for my thesis. So a few things I've done, I did comparisons, so I've got a few different implementations of the same thing. So a lot of them can be removed and it'll simplify it a lot. So in terms of the camera filters, I had a bunch of different implementations of the camera filter algorithm. So probably the best one is the one that's labeled as sequential. That's and the alternative one is the uncentered, the square root uncentered camera filter. Basically, the reason the sequential one is good is that it doesn't matter which order the object updates are performed in, whereas the other ones it does. You get a slightly different result depending on what order you're doing. So that one's a little bit more consistent. So, and so that's the class name at the bottom, just so you can find it. The merge metric, I tried out a bunch of different metrics to determine how close the models were together. And so you can probably get rid of a few of them. So there are 2 good ones, the Quinlan and Reynolds one, in the code. They give the most intuitive results. The other ones had some weird cases where ones that looked really similar didn't get reported as similar, and ones that didn't look the same were reported as the same. And they're also more dependent on the mean of the estimate compared to the covariance. If you're not using the merge bit, you can just not use that. So you might not need to worry about it. There are a bunch of different methods that I was using to do the branching part. So instead of doing all the options, I was trying to choose some a bit more, do a little bit of pre-processing to work out which ones were likely. None of them worked out great, so probably better off just doing them all. It's more robust anyway. So the exhaustive ones, just try every option and get rid of them later. That's the function name. So the other one is the pruning method, which is the way to get rid of them. There are a few of those as well. The best one is called the best one, and that's to keep however many best models. So it was the one I showed you the starting example. So it gives good accuracy, and it's much simpler than the others. Because you just got to sort them and then chunk out the bottom half of them. The alternative is the merging. It's a lot more complex to do the merging because you got to do this comparison between all the models. And then you basically need to use a threshold of similarity before you can get it down to a number that you're happy with. Because usually you want to reduce it to a certain certain number of models before you finish the frame, so that the next time you don't end up with a lot. Just because every time you got to do an update, it takes longer depending on how many models you use. And so that's the function for the skin pruning one, and you just give it a value and it'll get that many. Some other functions that might not be useful anymore. There was a function that does a 2-object update, and so when you see 2 objects, you can use the angle between those 2 objects because generally the angle of the object is a lot more accurate than the distance, and so you can use that measurement with a fairly low variance in order to get basically a good update that can make a good correction and get you into the right spot. Problem is that objects that we know the position of are pretty much disappearing now, and so that doesn't really happen anymore. So you might be able to get rid of that. But it used to work good when there were just the blue goals and the yellow goals and stuff.
It would at least get you down to 2 models, right? Like
Yeah.
one on each side of the field.
Do you think that could potentially be updated to something that could work with something where we only have a small number of potential matches for any figures?
Yeah, you could. You'd have to do each pair to do that test. But if you can set it down to 2 situations,
So split it into like a limited number of models. So rather than branching binary to branch into 4 or something like that.
yeah. But that's the reason this is really good is because basically the heading is usually pretty spot on, maybe fraction of a radian off or something. And so when you're looking at the angle between 2 objects, that's usually a pretty good measurement. Because even any errors are usually uniform, because they're due to like the head position or something. There was a function I had to remove ambiguous goal pairs. That was just to get rid of when there were too many ambiguous goal pairs. Because sometimes you get like 3 or 4, and you never used to be able to get that many. But maybe you might actually be able to get them. Sure. So just a briefly about where the comma filters are set up. Basically, the comma filter class is given a model, and the model contains the process equation and the measurement equation, which are those 2 nonlinear functions I showed before. And that's the only difference you have when you're applying it to a different system, basically. So, for example, with the robot one, you have the x, y, theta for the mean, and so for an observation of that, you can work out. You have a certain way of working out what the measurement should be for that state. And so, for a different system, that's a different equation. And the same with the process equation. The way it transitions from one step to the next step is different depending on the system. And so, the model just defines these 2 equations. And so the other thing is, like with the 2 object update I mentioned before, that's a different measurement type to the regular one. So there's 2 different measurement equations, observation equations, sorry. And so one is the angle between those 2 objects, and the other is the distance variant to the object, which are both you can work out based on the state of the robot and the position of those objects. And so you can add these new types, and basically all I do is when you call the update, you pass through what type of update it is, and it runs the appropriate function to get the estimated measurement for that measurement type. A few things that need to be done still. Basically, the shared ball thing hasn't been done that well. It's a little tricky calculating the covariance because it's dependent on both the robot's covariance and the ball's covariance because it's using the 2 models combined. And the other thing is incorporating that into the shared ball as well, because that's also dependent on the robot's estimate as well as the information you're receiving. Because the only way the robots can transmit the ball to each other is using the absolute field coordinates, because they're both based on the the other things that would probably be good to do would be to find a way, add a new update type to account for the line segments, as opposed to just the corners, which is always supported at the moment.
Is that right?
The corners are all of
The localization code is fine for it. Vision just doesn't report it.
Yeah, if they're reported, they can always.
Vision just doesn't see columns.
And lastly, you're probably going to want some sort of mirroring correction, I guess, which isn't there at the moment.
With the field line segments, would the large number of possible objects that can match cause a big correction issue? Because any arbitrary field line could match a large number of objects.
Yeah. So
Yeah,
it's a little tricky to work out.
There's 11.
There's a few different ways to do it. There's a paper that the Irish team presented that uses something diagrams. I can't remember what it's called. Yeah, to match a position on the field.
Yeah, but that assumes that you already roughly know your position, so it would be more like a odometry update.
But the other thing is if you keep the lines as just a one-dimensional thing, as in it's just y equals 30 or something, then it can sort of simplify the updating of you as well. Because you're basically assuming there's not actually that many lines when you do it like that compared to the corners in. And so basically the importance, so just like I was saying that it's important about the event-based stuff. So basically it's the ordering at the moment just is the game state check, the time update, the observation updates, and reporting the results. Basically the time update has to happen before the observation updates, because otherwise you end up with a case where it can correct to the correct position, and then you do the time update, and then it moves it because of odometry, and then you're in the wrong spot. So you want to do that time update, then do the corrections. Otherwise, you're just ruining the correction.
So is the time update like a single operation that's done for everything?
Yeah.
So if we do time update and there are no observations, would we just do another time update?
Yeah.
So could you just do a time update at regular intervals and just randomly throw in observations? Or would that break it?
The time update is dependent on our kinematics, right?
Yeah, so you basically want the time update to happen so that when you do the measurement updates, it's synchronized with the odometry.
The time update also needs to happen at the time you get that sensor information.
Yeah.
So it's time critical. Each sensor frame that comes in should trigger a time update.
Okay, so every
If
time.
any observations for that frame are there, that should trigger an observation update too, but only after the time update for that particular one.
Okay, so pretty much it should be a single threaded one where it does time update observation and then another time update observation.
Yeah.
And just keep
And that's fairly time critical, because if you do the time updates and the observations too far out of time with the information coming in, your estimates are going to be wrong.
Okay, so from an event trigger point of view, you do time update observation and recording. So 2, 3, and 4 would just be one operation that you do for every observation you make.
If the observations come in regularly or as a group, you can do a time update before you do them, I guess. But you also need time updates to when you're not seeing anything to moving with the odometry.
If the time updates are coming in much faster than the observation updates, though, to the point where it's not really an issue syncing, is it okay to just not do a time update while you're doing the observations and then do one after?
Yeah. So the time updates aren't that fast.
If you skip time update frames though, you're not going to correctly move. Because if you've had 10 things coming in saying that move 5 centimeters, and you skip a bunch of them, you're not going to move 50 centimeters in your return.
So basically, if you're walking along, say walk a meter, if you don't see any objects in that time, if you haven't done a time update, the robot new estimate will still be at your spot because it needs those time updates to move forward.
Okay, just say you do a time update, I don't know, 20 times a second or 50 times a second.
Yeah, that'd be fine.
And then you just do an observations as you saw them.
better bit, right?
As long as the
As
as long as the observations aren't old or
Yeah, so as long, also as long as you have processing that handle having time updates, it's like,
you just
The
you just
time
want to
updates are the fast bit, right, because they don't break.
basically similar to vision. You want the latest sensor data to go with the image.
yeah,
Does that make sense? Because otherwise your measurements are all.
yeah. So with the way it would work is as soon as the observation was made, it would be sent to localization. So either you have the choice of doing a time update and then processing your new thing, or you can just repeatedly time update all the time and just send in the observations as they're seen and assume that since the time updates every 50 times a second, you know that there can't be longer than that gap between the two.
You could lose sensor frames if you keep track of the extra amount of time that's had between two sensor frames in terms of doing that update.
Well, hopefully we should never have a case we haven't built up a sensor frame because where that would happen.
First, I'm saying you could discard it if you had to. You could discard a bunch of them and deal with the most recent, but
Yeah.
you need to keep track of how much time has passed.
So just some debugging tips. The stuff that can cause lots of problems. So basically, due to rounding errors, if the covariance matrix gets really small, you can end up with it going to 0 or
So negative. You can become too sure of your position and then crash.
and then it basically becomes not a number because it does inversions.
So is that the problem with your condition matrices?
Yeah, so there's stuff in there to stop that, but if you ever see not a number coming up in your results, that's probably the problem, is the covariance matrix getting too small.
Always be unsure of your position and crash.
Usually you can't be that sure of it anyway, so you've probably got a problem with generally increasing the measurement noise reduces the effect of an individual measurement update, but increases how long it takes to converge on a position based on those observations. So if it's seeing lots of objects and it's not updating much, then you might want to decrease the variance. If it's seeing too many and you're becoming too sure where it is, you might want to increase it. So basically increasing process noise increases the growth of the error ellipse. So basically if you watch localization and it's not seeing objects, you can see the ellipse expanding. Basically the process noise is what's doing that. And that's the noise that's assumed to be inherent in the model, that our model doesn't quite match reality.
Would that generally be lower than measurement noise?
Yeah. So it's usually low, but because it happens every single frame, regardless of if anything's seen or not, it generally has a fairly, it adds up pretty quickly, I guess.
It is actually important because when our robot goes around and doesn't see things for a long time, and suddenly he sees things, it is really, really lost. We don't want him to think that he knows where he is.
And so there's also noise that can be linked to the odometry as well, which increases more as you move further.
Do you know what measurements currently going
Into what?
into the localization in general? What things we currently use to work out our position?
The odometry, the observations, and then this information gain information for special cases.
Okay, so
The observations at the moment are only goalposts.
so I think goal faces not the only localization is based on the goal faces.
Self-localization, yeah.
Okay.
Say
So don't use the accelerometer or anything else. Or gyroscope.
That all goes into the odometry.
Okay. So odometry is sort of like an aggregation of sensor
All the
data.
sensor data.
Have you tested the accuracy of the load?
Yeah.
I don't know how much it's changed.
Okay. I'd love to know.
Not so great over more than 20 centimeters.
It's sort of a constant thing because every time the model changes, it seems to change.
Right.
Well, it'd be good if we had some tests for that. So.
And there's noise associated with that as well.
Yeah.
So you can add that.
Yeah, there are procedures for doing all of that. Say we could detect robots, how hard would it be to add seeing each other or seeing the opponent robots?
So you probably want to do it like before because it's another object that moves around the field. So it's
Complexity is you suddenly now make them confused.
Yeah,
So
because all
the
robots.
ball,
are
you want to be
engineered.
update the ball.
But then you
So anytime you see a robot, you could be updating any
Yeah,
of those.
I was thinking actually specifically first for our own teammates, is there a way that we could share that information easily and use it in an update?
If you can,
Yeah, if other teammates say where they are, can you use where they are and where you see them to be to update your position, or where you think to see them to be?
It's the other way around.
Or the other way around, sorry.
People would have to report where they see teammates.
Yeah, so where I see robots and you try and work out which one of the scene robots you, or if you are seen at all.
well, yeah, you could do that. You just have to do that like a regular measurement, like observation update. But you would have to use, so you'd be using, instead of this XY from just what we know of the field map, you'd be using their reported XY. But you'd also have to account for their variance.
What if they accounted for that when they were reporting? So you trusted anyone's reporting on position and
That's
variance?
perfect.
Not always variance, so their position and variance, you trust that their position and variance is correct.
So they have their own variance into the variance of their estimation of you, and then report that, and then you trust that they're reporting that at least accurately, and then just use that position and variance so that.
So you're talking about
The same
them
way we
reporting to
calculate-
you where they are.
Well, they're reporting to you where they think you are.
Okay. I was thinking of you, they reporting to you where they are and you working out where you are based on where they are.
Say you see a robot, could we use the same error calculation that we use for the ball and then send that model, you know, how
To everyone and say, I've seen a
codenames?
robot at this position, and then every robot says, okay, there's a possible measurement of me.
Would that work?
I guess so.
No, that would make Australia or the problems so big.
So you have to
That wouldn't work.
So the key thing is, then you've got your robot here, right? And he thinks he's somewhere in this region. You're standing over here. So he sees you, right?
Mm-hmm.
That's how it's working. Yeah. He gets his measurement, but that's also got a bit of an uncertainty area too.
Yeah.
So you need to combine that one and that one.
But that's the same operation that we have to do to the ball.
Yeah, which is the bit that hasn't really been done probably.
Oh, right.
So assuming that is done,
So if you do the ball one, then you can do that same on the robot one.
Yeah.
Cool. So how would someone go about doing that? So I haven't looked into it too much, but in theory it's just two probabilities based on each other. So you just need to work out how to correctly sum them to get the total covariance bit. The problem is there's some non-linear transformations between them.
The problem is combining the covariance, like the variance of twos.
Yeah, so how sure you are with your position and how sure you are
Yeah.
with the ball.
Yeah.
So the combination of that means that your certainty of the absolute position of the ball is worse than
I thought
your
the
relative
balls,
position.
certainly did change with your.
It
Oh, it does.
It does, but it's just fast.
I'm not 100% sure that's correct the way it's added,
Yeah.
but it is added. You might want to look at it though. That's the other one. And then you've got this other problem where one of the major things is, say you've got a fairly uncertain orientation, then all of a sudden, if your object could be anywhere in this range, you end up with this huge.
Right.
It could be anywhere in that huge area compared to this is. That's one of the.
It's pretty much when you turn the robot on, what the robot looks like.
And so, and if it gets too big, it ends up with some jump circles. So that's.
I suppose you could do a limitation and say, I'm definitely on the field somewhere.
Yeah, that's
Like the we've done observations generally, we've seen the goalposts recently, our error in there is actually fairly small.
But accounting for that orientation,
Yeah.
it or would be?
Because there's something like that.
It's a normal.
Like measuring Gaussian in another Gaussian. Like you may be somewhere on this Gaussian distribution, but there may be somewhere on here. It's the convolution.
Okay, the problem is it's not the same.
It's a nonlinear space.
It's not the same coordinate
Like
systems, and it's a nonlinear transformation between them.
Okay.
Is the trouble.
Yeah. So it is a convolution, but it's a convolution through different nonlinear spaces.
So a convolution with non-linear transforms. There's also a different dimensionality too, because your ball just has a 2D position.
Yes.
And the robot
And the ball has a velocity too.
That's a prediction result of the Kalman filter, isn't it?
It's actually, it's calculated as a statement of problem.
But it's not something you ever measure.
No. It's measured by looking at the different positions of the ball.
Yeah, well, you get a three-dimensional Gaussian because you have X, Y, theta.
But why can't you project that onto a two-dimensional Gaussian?
But then, what is interesting in our position relative to someone else's position? Isn't it just X, Y?
No.
So we know we're standing here, we see someone else standing over there. So
Yeah.
relative to us, X, Y, they're over there somewhere.
So you've got a lift,
The
but it's
problem
like
is,
a,
I don't know whether we're facing this way or say.
it's not actually a lift.
So it could be anywhere in that arc, X, Y rotated around.
You can do it at the 2D level, but then you have to bring it back out to your orientation.
Yeah.
Because relative to you is fine, but everyone's determining on absolute values.
Just
Except
think
for
of the extreme. If you see a robot and you say, okay, it's a meter in front of me, and you report that position, but you're 180 degrees off, then you reported a completely different location already. Right? Because it's actually 2 meters away from.
Yeah.
where you reported.
Practically, we can probably get away with just projecting like a sideways Gaussian up to the distance and forgetting the curvature, because the curvature will generally
Should
be
be
small. Or we shouldn't be reporting.
Well, it's like more than 20 degrees.
Yeah, if it's more than a few degrees, then we're just gonna mess things up and we want to ignore that.
Yeah.
So you can probably make a linear.
In the end, Brendan, your heat map will just look like a robot sitting with a giant ball circle around it. This stretched ball around it. The ball is surrounding you.
I have the ball.
So, is there any other questions?
So it'll be interesting, because there's okay, the ball's right here, I've sort of got a ticket now.
How did you go about, well, like you tested a whole bunch of various mechanisms. And so how do you test the reliability of the system now? Because we use board for it.
So basically, I had a bunch of different data sets, which I ran the robot, got all the vision inputs, all the geometry, all the sensor data, record them to logs.
Yeah.
Then I ran the different systems with the different options, and then compared the accuracy and the processing time and that sort of stuff to determine which one to look at.
So we don't have access to that.
I can give them to you. There's a lot of logs. It's
One of the things I wanted to do is, well, we've got two things that will help. One of them is I wanted us to be able to hook into SimSpark so that we can simulate tests, because I know you do a lot of that.
yeah, I did mine in simulator because it's a lot of hassle going to get.
The other thing is, when we get the motion capture system set up, we'll be able to use that to track the robot's position and see what we are.
So
We can figure out what
that might actually be some
transformers aren't working.
what you asked me about too. In the simulator, it gave the XY position and the orientation of the robot is measured by the simulator, so you can get it against that to know where that should be. And I went through every frame to check how close it was to that, and then the average error and what to work out which one as well. So mostly it was a case of, with the ambiguous stuff, it would basically choose the wrong option and get stuck there. Was usually the main difference. Like one of the systems would have a major failure.
Right.
And so basically, one of the main conclusions of my thesis was the main thing is how many models you keep, not how you keep them. Because basically, the more possible branches you've got at any time, the more likely it is you have the correct one.
So we should tune that
for efficiency and
In
accuracy.
practice, we actually go the opposite way to try to break symmetry, but that's just because we don't have anything to deal with the fact that we can't tell which.
One thing with this invest one, I think I've got a version of the final version of the final set of code I used to do all my experiments. But I had an extra part where it had a tendency with the invest one where it would end up with like 6 models, but they're all virtually the same. And so I had a function that went through and checked if that was the case, and then got rid of repeated models that were the same thing.
So that would be just merging, wouldn't it? So it's like a combination of merge and discard.
Yeah, I just went through and said, well, these are pretty much the same, so just add their values together and try one.
Yeah, so having a merge and discard. A merge would help to start gaining heaps of the same models. And that would pretty much get you stuck because
That's probably the one advantage the merge had. It would often reduce to less models than the invest one, because the invest one had a
also
hard limit where it was at every time.
how much does the performance get impacted by having more models?
Fair bit.
So more models is exponentially grows worse.
Yeah.
Unless we have a whole core for localization.
Well, we can do that.
Because like if you have a decision that's just taken 2 ways, if you start off with 8, then you end up with 16 possibilities. If you start off with 4, then you end up with 8.
I'll put it this way, I had a problem once in the vision system where I wasn't clearing my corners that I found before I reported the next set of corners. And you should have seen the localization runtime graph.
It was exponential.
Yeah, and it started taking like 20 to 30 seconds per frame to process. At which point the robot just seized up. But yeah, it just grew exponentially. And you could literally see exactly when I'd done it because there was just a massive instantaneous bump. And then another bump. So I wasn't reporting it for large time, and I think I only got up, I was only in the 10s field lines that were being recorded, like 60 or so field lines.
That's a lot of field lines to see. A robot.
Your thesis were useful for us to read that in the program.
Possibly. But, I can send that to Josiah.
Yeah.
Along with the slides.
Yeah.
One of the other things with taking this on is I'm doing a course now that's one of the hardest courses I've done yet, and it gets to Kalman filters at the end when we only do linear Kalman filters. So, like, this isn't easy or trivial stuff at all.
So I left out most of the equations.
Thank you.
Yeah, I understand.
Basically, if you think that's not too hard, I can probably improve on the equations. Just stick with porting it over first and looking at what extra information
And I think
we're going to look there.
I can improve the performance, but I'm not
When I sent you my thesis, there's a chapter on derivation of the common filter that's used.
Yeah.
Did you look at particle filters?
Not recently.
What's your take on them versus the multimodal Kalman filter?
They're pretty competitive, I think.
Which one's faster performance-wise? They're pretty much the same.
Depends how accurate you want the particle filter. How many particles you want to use.
I guess it's the same with how many models you want to have.
Yeah, it's the same sort of thing. But, so generally the trade-off is common filters can get more accurate with less resources, but they've got more trouble with the ambiguous stuff. Because with particle filters, you do lots of thousands of particles.
Then you just update them all equally, don't you?
And you have to run update for everyone.
Yes. And the nodes just
Okay. Would be worth looking at combining the two approaches, having multimodal Kalman filter for objects that are known, and then keeping ambiguous objects for the particle filter.
No, because then you'd be running two localization ones. Because I mean, what you're running the filter for is your state, which is your robot's internal position state and velocity state, and the ball position velocity state.
Yeah, but I'm thinking more about robots where you could have a lot of robots that you could possibly potentially see. Particle filter might work better with keeping track of robots because telling you to do
I think that's what the Google software uses the particle filter.
Yeah, it uses
Pedestrians and things like that.
Yeah.
So yeah, can you
So it's got that exact same thing. They toss up between carbon filters and particle filters and apply them in different situations.
Yeah, so it might be worth one down
So
at
this,
least applying both.
the localization with rotocarbon, a lot of the time the particle filters have to use a lot of tricks, like, when they're doing their research, they have to place them in certain spots and things to make sure that they've got enough of the ink covered because they've got don't have enough particles to really cover the space.
Okay.
So there's a lot of things that are going to be.
Could you see the particle positions based on your Kalman filters, alternative Kalman filters? To place them in spots? Because the two options don't seem to be mutually exclusive.
No, so
Because you can use the particle filters as an input to the Kalman filters, and you can use the Kalman filters to help weigh the particles.
Don't think you have the resources to run both.
And if you could, I think the trade-off would be you'd be trading a lot of resources for a fairly small gain, whereas you could just contribute more resources to one of the methods and get a better gain, I think.
Okay.
I mean, that's one thing you can test, but that seems like a
I'm
pretty...
on that.
implementing a particle filter just to test that seems like a big thing.
at one stage, I think, I'm not sure if they still do it, but I'm pretty sure they use both. One was for the ball, one was for the robot.
Okay. Yeah, that's what I was thinking. So you localize less things in each system.
Yeah.
I think they use a particle filter for the robot and a current filter for the ball.
Yeah.
But that's where you might have to find a hybrid type system.
I think the best of both worlds.
But again, that's a fair bit of extra work.
Yeah, that's enough.
Adding a whole other
So, I guess, any other questions? So just quickly, one thing that might help you understand one bit a little bit better. So with the ball and the velocity, for example, with this function here, which does the time update, one example with the ball is when it does the time update, it adds the velocity times the time to the position. So it basically moves the ball by the velocity to get the new position.
By the internal velocity
And so that's an example of the sort of thing that function is responsible for. Because it updates it to say this much time's passed, the ball is moving this fast, therefore the ball is now here.
How about the error in the velocity of the model?
It's actually fairly good.
Yeah. Once we switch to
Does that account for like drag?
Yeah, there's just a decay on the speed, and that also happens in that step where the speed gets reduced and has to get put back up over known observation.
If you were to suggest a first thing for someone who wanted to get into the localization system and start learning it and changing it, what would be the first most simple change you think someone could attempt?
Probably go through it and remove all the code that don't need anymore.
But in terms of like some added feature or some fix, that's what.
Well, I think they've learned a fair bit, like
just
putting it into the new system, just in terms of where stuff happens.
How would you tackle that?
If you have any other parts that need a Kalman filter, that might be a good spot to just get a general.
so grab the power filters and
Yeah, because we wanted to put the Kalman filters on that input, like the accelerometer, gyroscope, and things like that.
So basically, the way it's set out now, I don't know if you want to change it or not, but the way it's structured is I have this model class, which is a model of the system you're filtering, and it just has these two equations. Basically the f of x, xu, and h of x.
So one of them's the
And all they need to do is, this one needs to convert from needs to calculate the new estimate based on the old estimate and the input. And this one needs to calculate the measurement based on the state. So
do you have some of these functions that already lie around somewhere?
yeah, so there's already ones for the robot, there's already ones for the ball. So if you want to apply it to, say, a different type of system, like you just need to write a new model class, which has these functions. And so basically, and then the Kalman filter algorithm just uses them to calculate the.
So say we're applying it into a situation where it's just a typical linear Kalman filter would be fine. Is there a way we can write those functions where it'll basically
Return to a linear case, where you would just write the equations as linear, I guess.
Yeah.
You probably would just want to use a linear commutator, like less computation.
I think what's a linear commutator is n is something, UKF is squared, and EKF is a bit more.
Yeah.
It's n squared rather than something.
What's n? What's n in this case?
If you want, I can
say space size or something.
If you're interested in, I can explain what the difference between these two are and how they get around the non-linearities.
Shannon loves it. Shannon's doing this stuff.
Basically,
This is only helping me.
the standard common filter linearizes around the point it's at. So if you've got a curve like that, it'll just linearize this part and then calculate the changes based on this. The uncentered common filter uses a bunch of sample points. So say you've got a position here and then there are ellipses here. It'll sort of choose a few sample points around here that are weighted. And then it moves those points based on the nonlinear equation and then recalculates that variance. So you can go from, you can capture nonlinear changes in the variance. But it always goes back to a Gaussian distribution.
Okay, so yeah, bumps it up into a multimodal distribution sort of, and then normalize it.
Yeah, and then it basically processes each of the points in the domain. Instead of using the mean covariance, it just uses this bunch of things. So it's sort of like a little particle curve.
Yeah, it's a little mean part of it. Spawns and dies.
And then the uncentered one's actually pretty easy to implement as well because you just need to. So with this measurement equation, that just gets to apply to each of those samples to get the converted samples.
There really is a whole bunch of linear ones.
And so what you
No,
regenerate a new mean and variance from those samples after
Yeah.
they've been updated.
Yeah, there's basically an equation to generate the samples from a mean and variance, and then an equation to calculate the mean.
Set back. Okay.
Yeah, and this one just has a, just linearizes the curve and just uses that as the. So if it's highly nonlinear, it usually the uncentered works well.
So the geometry section, the part of the code where we're mentioning the geometry, where does that exist currently? Do you know?
One of the sensor parts.
Right.
I'm not even sure where in the current system the sensor data is actually filtered into something.
There's a class that does a whole bunch of things. It reads the runs, I think, checks the flow and stuff.
Oh, that class.
Yeah,
That's
it's in
horrible.
there.
Yeah, I don't know what that class is.
It's
I'm not
basically-
sure I want to.
There's a mega class that lives somewhere out in cyberspace and it does a lot of things.
It basically does all the sensor processing when the sensor values come in.
Okay, so sensor values come in and then it goes nuts.
Anything that's not a raw sensor value gets calculated. So
Okay. Yeah, we'll give me one of those.
does kinematics, so that's the thing.
Oh, so it's
Pretty much everything.
Yeah,
like
it
that.
kills the kinematics.
Really glad we do.
If you have any resources, links, papers, etc. that you use to research and learn all this, that would be
Probabilistic robotics by,
I think oh no, we don't have that one.
The only one someone would have actually read.
I'd probably recommend that one.
one of the authors is data sorts.
Is
Yeah,
there anything
so
else?
probably not, like specifically focuses on what.
There's the river part.
Yeah.
It's pretty good, but it's skips out all the.
I don't know about where you look around
There's
that.
this that actually explains the math.
That one isn't good.
Right.
There's no one with yellow dots on it.
Oh, I've seen that in the lab.
Yeah, it's somewhere in the line. Or was.
There's,
There's got particle filters in it as well. It covers pretty much all of the localization parameters.
of course, it's
44 cents.
control system design. Oh, cool. So it follows on from the really, really easy 45.
Oh yeah, I
And
know.
it just works out.
Great.
I don't think the content itself is that difficult. It's just a lot of assumptions Basically assumes you're a mechatronics student.
There's a lot of science too.
Yeah, they've got 3% and submit like 10-page reports.
Oh, I know that's
And then a 2% lab that's taking you 15 hours.
Yeah.
Long story short, it's possible you learn more quicker from C.
So basically, it covers the state-based stuff, doesn't it?
Yeah, sort of.
4500s of like.
And the controllers, and then the state estimators, and then sort of culminates in the
Observers and then
controls.
deadline on time.
Yeah, yeah.
Because that's
And
one
you
called
can't do
observer,
anything.
isn't it?
Yeah. So it's basically one of the best state estimators or any system.
And 4410, the way it does it is probably not so helpful in terms of understanding the stuff and its application to localization.
It's weird. Once you see how it fits, it seems really obvious. But when learning it in 4410, it doesn't sort of, you can't put it together quite easily. But once you sort of figure out, well, that's the state, that's the input, that's the output, then it all of a sudden makes sense whether you can use it for that so easily.
Any questions, guys?
So, do we have action items?
Okay.
Do we want to do it now?
Action items.
Yeah, well, I've got so far. The only one I've got is Shannon Brennan signing at page 8.
For service and road.
Keep it at the socks.
Oh, you're
So I would really like for us to start working on causing parts of this system over. I think with localization, Steve would probably be happy to help if anyone wants to. What?
Yeah, it's unrelated stuff.
Right.